All right, so we're moving on. Should have closed my email out. That's that beeping you hear. So, gonna look at, if you remember from last week, or last week, I think it was Monday's lesson, I showed you there's two ways to find derivative. So the first one I said we could find the derivative at a point. So if we want to find the derivative at c f of c, then we did the problem this way: limit as x approaches c of f of x minus f of c over x minus c, and that tells us the derivative at that x value. It's not a formula; it just gives us the actual slope. So this gives us the slope of the line there, and then we use delta x goes to 0, and we use this here. So let's make sure we understand the difference in these two. This tells us the slope of tangent line at x equals c. It gives us the actual slope. So I'm going to give you a numerical value. This, because you're going to have x in your answer for the most part, is a formula for slope of tangent line. So make sure we understand the difference there, okay? That one of them gives us the actual, the numerical value, one gives us a formula. Notice they're both going to be tangent lines because both of these formulas are slope. They're both change in y over change in x. See, those are y's, those are x's. Change in y over change in x. And we're trying to get the 2 points to approach each other. So whichever way you're looking at it, both of these are giving you a tangent line there. Okay, so now here's the question for today. Let's just say we take this function. So a couple things I want to show you is, one, this formula the second formula is not going to work. We'll talk about why it would be difficult to use. And then the second thing we're going to look at is show you that it doesn't exist somewhere because there's a sharp turn. Okay? So if we look at this graph, absolute value of x minus 2, you know what the graph looks like. Okay? It's a V shape. Like that. All right, there's that. Okay. Then, so let's say you want to find derivative. Now, if you just think for a second, you shouldn't have to, remember what I said, the other day I said, don't think logically, just do calculus and get the answer. Then I said, if you think logically, I said from now on we need to think before we do the calculus. I said, just that one time I wanted you to do the calculus. Look, to the right of 2, what do you think is always going to be the slope? 1. Always. To the left of 2, what's the slope? -1. That's the answer. But how do you write that? How do you get a function for that? So, anyways, so if we try, say we're going to try to find the derivative. Here's where we run into trouble. X plus delta x has to go in for x. So I'm using the second formula here. Minus absolute value of x minus 2 all over delta x. And now the problem we run into are the bars. That is in the bars, and we can't make any kind of substitutions. We don't know if this inside, if it's positive or negative. How do we do? So the problem that we run into is because we're stuck in these absolute value bars, we cannot make any simplifications from here. So we're stuck. This way is not going to work. Okay. So we have to have another way to do this. Well, the other way is this, is we can just find the derivative at a point. So I'm going to prove to you that at 3 the derivative should be 1. And then I'm going to prove to you that at 2 it doesn't exist. Okay, but we'll show a different method. So, all right, so does everybody understand why we're stuck here? Once I plug it into these bars, all that is stuck in the bars and I can't make any simplifications. So this method is not going to work for us. So we're not going to get a formula for slope. we're gonna have to just rely on just the slope. So we're gonna erase this difference quotient for now. We're not gonna be able to use that. So now what I wanna talk about is this. With any limit, if you're gonna approach a number, all right, because C is gonna be a number, we can break the limit up two ways. We can approach from the right, and we can approach from the left. Okay, so that's what we're gonna do. We're gonna do each of these separately and see if we can get an answer from here that makes sense. And so those two, what should happen is they should equal to the same number. We should get the same value. If we don't, then it's a does not exist. We need, and if we're gonna work the problem like this, we're gonna approach from the right and we're gonna approach from the left, and we should get the same answer, okay? And this is called, the nickname, or not the nickname, but another way to call this is, I'm gonna run this right here. When I write it like this, it's called the derivative from the right. And this is called the derivative from the left. And if those are equal, so if those two are give the same value, then it exists. Okay? So it's just normal limits that we're going to be working with. Okay? So if the limit as x approaches c from the right is equal to the limit as x approaches c from the left, then the derivative exists. So I'm going to do two problems to this. So what we're going to do, so we're going to have to forego this method, and we're going to work two separate limits. I'm going to prove to you that it exists at 3, and we all should know the answer. What's going to be the slope at 3? 1. That should be our answer, if we do calculus properly. And then I'm going to prove to you that at 2, why I'm going to show you that it doesn't exist, and it's going to, now you're going to take a note that anytime I have a sharp turn, that the derivative doesn't exist, okay? So here's what we're going to do. We're going to do each of these. We're going to approach 3 first. We're going to do this one, okay? So we're going to take the limit as x approaches 3 from the right of f of x minus f of c. And let's see, f of c is absolute value of 3 minus 2. So I actually plug in the 3 over x minus 3. What am I doing wrong here? Something. Make sure I'm doing everything right. So our c is 3, right? F of x minus f of c, yeah. That should be it. Okay, good. So far it looks like I plugged in everything right? Okay. So now let's see what happens. Let's do this one together. We can do the other one. I get absolute value of x minus 2 minus 1 all over x minus 3. Now, I'm not too happy right now. It shouldn't be this difficult. Well, we can look at it like this. So I can't, obviously I can't do, I know that this answer is 1. Let me show you. So let's look at it like this. How can I see that this comes out to be 1? This looks awful, by the way. But instead of plugging in, just plug in a 4, because we got to approach 3 from the right. If you plug in a 4, what do we get? So just imagine if you plug in a 4, all right? Then we'll plug in like a 3.5. What happens? You get 2 minus 1, which is 1 over 1. Okay, that's 1. Plug in a 3, because it's 3 from the right, so even if you plug in a 3.1, it's the absolute value of 3.1 minus 2 minus 1 over over 3.1 minus 3. So let's look at what happens there. This becomes 1.1 minus 1 is 0.1 over 0.1, it's 1. So I can see I'm always going to get 1. Okay, so this equals to 1. All right, not pretty. It's hard to look at it algebraically. It's easier to look at it numerically. So if you do the limit as x approaches 3 from the left, it's going to be the same thing. Absolute value of x minus 2 minus, what was it, 1 over x minus 3. Now let's see what happens if I plug in like numbers left of 3. So I'm going to just pick a simple number left of 3. I'm going to pick 2 just to plug in and see what happens. Now remember, I have to get 1 again or it doesn't exist. So now I'm going to plug in, I'll plug in a 2 because 2 is left of 3. If I plug in a 2, the top becomes -1, the bottom becomes -1, and a negative over a negative is a positive and 1. So no matter what, whether I approach 3 from the right or I approach 3 from the left, I get a 1. Okay? So that means that f prime of 3 is equal to 1. So the slope here is 1, which we knew that anyways. That's not the point of this problem. The point of this problem is to show you that it doesn't exist here. Okay? Now, so does everybody see that I didn't really try to do any algebra here? I just plugged numbers in and thought about it like that. Okay? All right. So now, we'll erase that. Let's move over to here and see what happens. So here's what I want you to do. The limit as x approaches 2 from the right of your f of x minus f of 2 over x minus 2. So fill that in, set that up, and the limit as x approaches 2 from the left of f of x minus f of 2 over x minus 2. See what you did for each of those. So that's right here at that sharp turn. And I'm going to show you that we're going to see what happens. So what's the name? What are we finding right here? What's the technical calculus name for this? Derivative from the right, and this is? So we're going to basically see what's the slope here and what's the slope here. If we have a smooth turn, those slopes are going to be the same. If we have a sharp turn, you'll see you'll get different slopes. Okay, that's what we're going to find. So you guys sub in f of x, sub in your f of 2, and see if you can simplify this. I would just plug in numbers, like something bigger than 2, like plug in a 3 for the 2 from the right. And we're going to erase this. So substitute in your f of x and your f of 2. There was something else I said we needed to talk about today. It was, some notations. Okay, we're going to do that. So now we're working this problem here. Not the 3, we already did that. Do this. So we're trying to find now f prime of 2. Okay. So I'm going to at least write what you should have. F of x is absolute value of x minus 2. What's f of 2? 0. Over x minus 2. So look, just plug in like a 3. Plug in a 2.5 and look at what your fraction is every time. You're just trying to see, you're either going to get 1 or -1. You're trying to see what is your answer there. Okay. So, namely, let's look. If I plug in any number bigger than 2, that top is going to come out like, so if I plug in a 2.5, right, to the top for x, the top is going to come out to be what? Let's say we plug in a 2.5. 2.5 minus 2 absolute value, you get what? 0.5. And then 2.5 minus 2 on the bottom is 0.5. So any number bigger than 2, what's this ratio always going to be? Positive 1. That's the point of this. Any number less than 2, what's this ratio always going to come out to be? No. If it's less than 2, it's always going to be what? I heard 2 answers. There's just 1 answer. If it's less than 2, I only get 1 answer. Negative 1. That's exactly right. You only get negative 1. So let's say I plug in a 1.5, right? I get absolute value of negative 0.5, right? Absolute value of negative 0.5 over negative 0.5. So the top is always, the numbers are going to be the same, but the top is always going to be positive. The bottom is always going to be negative if I'm picking numbers left of 2. So that's negative 1. So now this is the definition of a sharp turn. Now you have proven that there's a sharp turn. Because the slope on one side is 1, the slope on the other side is negative 1, and that means a sharp turn. So since the limit as x approaches 2 from the right does not equal the limit as x approaches 2 from the left, and we're doing derivatives, derivative does not exist. Sharp turn. That's how you know you have a sharp turn. And sometimes you got to use this test because sometimes we won't know. Like on absolute value, it's obvious that's a sharp turn. It looks sharp. Well, I'm going to show you another problem here that we're not sure if it's a sharp turn or not. Notice this right here. When we did the derivative formula, we got this, right? When we did derivative, we got absolute value of x minus 2 over x minus 2. Actually, if we graph this, so I want you to see, I'm going to graph that right below here. Notice the graph is this. It's the which way did he go, George? See? That famous graph is always the derivative of absolute value. Because think, is it 1 from the right of 2? Yes. Is it negative 1 to the left of 2? Yes. This is the graph of that, of the derivative. This should tell you the slope. Right of 2, it's 1. Left of 2, it's negative 1. At 2, cannot get an answer. Okay? So the which way did he go, George, is the derivative function for absolute value. Okay? All right. So what do I have to have happen if I'm not sure if it's a sharp turn or not? I got to get the same from the right and from the left. So you're going to say, well, aren't you going to just know it's a sharp turn? Not always. Okay? So here's a different problem. Let us take a piecewise continuous function. So we're going to take a piecewise continuous function, and we'll call this example 2, and we'll say given f of x is x squared for x less than 1, and 4x minus 3 for x greater than or equal to 1. So first of all, this is piecewise continuous. Okay? The $60 million question is, how do I know it's continuous if I have a piece of one graph and a piece of the other?
They evaluate the same.
Yeah, so if you plug in a 1, so what Elijah's saying is, look, if we plug in a 1, that has the point 1, 1, and that's an open circle. And if I plug in a 1 here, that has the point 1, 1, and that's a closed circle. These two should connect, like Legos, or like there's rods that snap together, okay? Connects, or whatever these things are called. So if I just look at the picture real quick, I basically have x squared left of 1, and then I have 4x minus 3, which goes here. I have that line. So the question is, if I want to find the derivative here, right here at 1, is that a smooth connection or is it a sharp turn? See, so we're going to be asked we're gonna have to find f prime of 1. Okay? So we're gonna use the same mentality we just did that we did with the absolute value. We're gonna use that alternative form. We're gonna do the limit as x approaches 1 from the right of f of x minus f of 1 over x minus 1. Now look, if I'm approaching 1 from the right, I'm on which function? The parabola or the line? The line. So when you set this up, you've got to plug that in for f of x, because you're right of 1. And then you're going to do the limit as x approaches 1 from the left. And you're going to do f of x minus f of 1 over x minus 1. And when you're left of 1, you're on which function? The parabola, you got to plug that in. So this goes into this problem, and the x squared goes into here. Because look, on right and left of 1, you're on 2. And you're going to see what is your slope as you approach 1. And we have to approach the same slope to show that this is not a sharp turn. Okay? So work each of these out, and let's see what your answers are. And you be able to use common sense on the first one, but you can still work it out. It takes 2 seconds. Okay. Okay, let's go ahead and get started, because I'm, again, pressed for time on the film. So, we're trying to find just the slope at 1. And either we're going to have a slope, or it's a sharp turn and it does not exist. But it's hard to tell, because you can't really visualize this graph. You can't look and say, oh, I see a sharp turn there. So, I'm going to use this is called the alternative form, when we don't use delta x. We're just finding the slope at 1x. So if I'm going to approach 1 from the right, I'm on the linear function, and we should always know what the slope on a line is, right? Minus f of 1 is 1. So when you get this, you say, well, how do I work this out? Well, look, it becomes 4x minus 4 over x minus 1. And notice, I can factor a 4 out, and that's what's creating my hole there. I'm running low on room, so let me drop right here. So I can factor a 4 out, and that leaves me with x minus 1 over x minus 1. So if I try to do direct substitution, I could get rid of that, and now I can see that the limit goes to 4. So the slope, a little to the right of 1 is 4. So what I have to have is a slope a little bit to the left of 1. It needs to be 4, or it's a sharp turn. Well, now when I plug in left, I'm on the parabola. So when I do this one, left of 1, I'm on my parabola there, so it's x squared minus f of 1 is 1 over x minus 1. And again, even though it's a one-sided limit, I can still do direct substitution from those techniques. And the technique for this is what? What's the technique to solve? Yeah, so you just factor it, and if you factor this, x minus 1, x plus 1 over x minus 1. The x minus 1's cancel. I can do direct substitution, and I get 2. And because I got two separate answers, the derivative from the right is 4, the derivative from the left is 2. Since those are different numerically, we have to say the derivative does not exist. So f prime of 1 does not exist, okay? So just to show you where it would, rather than working the whole problem, again, if I change the second function slightly, and I made it 2x minus 1, notice they still have the point 1, 1, right? So it's piecewise continuous. And I wanted to find f prime of 1. So notice, limit as x approaches 1 from the left of this x squared here, it's still going to go to 2. Now look at this one. If I do the limit as x approaches 1 from the right of that, what's always the slope on that one? 2. You would get the same answer, and then you would say, oh, it's 2, it's not a sharp turn. So it just connects just right, so it's a smooth connection. Okay? Basically what this one's doing, the way it's connecting, it's more kind of, probably this is kind of more like this, and then it's kind of more like that there, and it's got a sharp of what's going on right now. Okay? All right, I'm going to point, you're going to tell me what this is called. What's this called? Derivative from the right. This is the alternative form of the derivative. This is what? So in order for the derivative to exist at 1, they both have to be the same. Okay? And you use it in those situations. All right. So the last thing I want to do is just go over some notation. When I was talking to the guys at home, just wanted to go over some of the verbiage. Does everybody see any questions about this process? Okay, you'll have a couple of examples in the homework. So tomorrow when we come in, we can pull the homework up and look at it. All right. So at the end of 2-1. Okay? It's at the end. So any that you're not sure about in there, we can look at. All right, please ask. All right. All right, so now the last thing I want to do is just go over some terminology. So if say our function is x squared, one way to write the derivative is this, f prime of x. That means the derivative, and the derivative, remember, stands for formula for slope of tangent line. I want to give you all the notations right now that we would use, okay? So that's one notation, we use f prime. Had I written it y equal to x squared, we would have written y prime is 2x. So f prime of x and y prime are two ways that it means the same thing. So the prime mark means that's the notation for the derivative. There's a third one that looks a little weird, but I'll show you that it makes sense. It makes sense. So here's the formula we use, the difference quotient to find that derivative, right? We use this. Now, so technically when we want to find the formula for slope, we use this difference quotient. What is the numerator? What can you call the numerator? Just the numerator. I would say I'll give you a Kit Kat for this, but that's already happened, so you got to earn the Kit Kat. What can you call the numerator? Well, what do you call the denominator? Change in x. What do you call the numerator? It's a change in y, because it's two y's being subtracted. But there's a symbol. So in lieu of using this, because this is what we use to work it out, I'm going to go with symbols now and show you a different symbol, a third symbol we use for derivative. So this could be written, if I wanted to just shorthand it, it's change in y over change in x. And remember what we're trying to do, whatever your curve is, right? You're picking a point at x, you're moving delta x here to another point. And if you're finding slope, then you're finding change in y over change in x. You're seeing what that slope equals. Well, remember what's happening. That point isn't staying there. That point's moving where? This point right here that I'm pointing to is going to move where if we're finding derivative? What's the whole point? You don't want 2 points for a tangent line, you want how many points? One. So I'm moving this point where? No, not both ways. At x, I'm moving it towards x, right? So as I move it towards x, what happens to the change in x and the change in y? Do they get bigger or do they get smaller? They get smaller. They get very, very small. We say infinitesimally small. They're as close as you can get to zero. So what happens is we have when we work this out, we get a very small change in y over a very small change in x. I mean, that's basically what we're doing, and we're looking at what that ratio is, right? Because it's very small, because we're trying to get that point very, very close to that one. Well, we have a symbol for that. Instead of using delta y and delta x, we just say it's dy over dx. And that is the third way to write a derivative. So the third way you could have written it is dy over dx is 2x. Very small change in y over very small change in x. Okay? And so these are the three. If it's f, we call it f prime. G, we call it g prime. Y, we call it y prime or dy over dx. And what does it stand for? A very small change in y over a very small change in x. And that now really, when you see it like that, correlates more to a slope. Okay. And those are your three. And this, you'll see this word, this is called Leibniz notation. You'll use this notation for other things, but I just want to get that. Okay. Stop this because my battery is. All right, that's it for this lesson.